In 1971, physicist Joseph Haefel and astronomer Richard Keating boarded commercial airliners carrying 4 cesium atomic clocks, the most precise timepieces available. They flew around the world twice, once eastward, once westward. When they returned and compared their clocks to identical clocks that remained on the ground, the traveling clocks showed different times. Not by milliseconds, by hundreds of nanoseconds, measurable, predictable differences. The eastward clocks had lost 59 nanoseconds. The westward clocks had gained 273 nanoseconds. Time itself had run at different rates. This wasn't instrumental error. It was predicted exactly by Einstein's theories of relativity. Moving clocks run slow. Clocks in stronger gravitational fields run slow. Time is not absolute. Right now, GPS satellites orbiting Earth experience time differently than you do. Their clocks tick 38 microseconds faster per day than clocks on the ground. Without corrections for time dilation, GPS navigation would accumulate errors of 10 kilometers per day. Your phone's map works because engineers account for Einstein's equations. Astronauts on the International Space Station age slightly slower than people on Earth, about 0.007 seconds less per 6-month mission. The difference is tiny, but real and measurable. At extreme speeds approaching light speed, time dilation becomes dramatic. Travel at 99% the speed of light, and time slows by a factor of 7. 1 year for you equals 7 years for everyone else. At a black hole's event horizon, time dilation becomes infinite. From a safe distance, you'd watch someone falling in, slow down, redshift, and freeze, never quite crossing the horizon, their image dimming eternally. But from their perspective, they'd cross in finite time, experiencing nothing unusual until tidal forces tore them apart. Time is malleable, relative, frame-dependent. What seems simultaneous to one observer occurs at different times for another. Today, we explore how time itself breaks down under extreme conditions. We examine the evidence that proves time is not what it seems, and we confront the reality that past, present, and future are not universal concepts. They're local. In 1905, Albert Einstein published On the Electrodynamics of Moving Bodies, the paper that introduced special relativity. He started with 2 simple postulates. 1. The laws of physics are the same in all inertial reference frames. 2. The speed of light in vacuum is constant for all observers, regardless of their motion. These assumptions sound innocuous. Their implications are revolutionary. If light speed is constant for all observers, then space and time must be flexible to compensate. Consider, you're standing still, watching a train pass at high speed. Someone on the train shines a flashlight forward. From their perspective, light travels at c, 300,000 kilometers per second. From your perspective on the ground, you might expect the light to travel at c plus the train's velocity, but it doesn't. Light still travels at exactly c from your perspective too. How is this possible? Time must run slower on the moving train. Distances along the train's direction of motion must contract. These effects, time dilation and length contraction, adjust exactly to keep light speed constant. The mathematics is straightforward. The Lorentz factor gamma describes time dilation. Gamma equals 1 over the square root of 1 minus v squared over c squared, where v is velocity and c is light speed. At everyday speeds, gamma is negligibly close to 1. At 100 kilometers per hour, gamma equals 1.000000000043. Time dilation is 1 part in 100 billion. But at 90% light speed, gamma equals 2.29. Time runs at 44% normal rate. At 99% light speed, gamma equals 7.09. Time runs 7 times slower. At 99.9% light speed, gamma equals 22.4. As v approaches c, gamma approaches infinity. Time would stop completely at light speed, which is why nothing with mass can reach it. Einstein's theory produces a famous thought experiment, the twin paradox. Imagine twins, Alice and Bob. Alice boards a spacecraft and travels to Alpha Centauri, 4.37 light-years away, at 80% light speed, then returns at the same speed. From Earth's perspective, the trip takes 10.9 years, 4.37 times 2, divided by 0.8. Alice experiences time dilation by factor gamma equals 1.67. For Alice, only 6.5 years pass. When she returns, she's 4.4 years younger than Bob. This seems paradoxical because from Alice's perspective, Earth is moving away and returning. Shouldn't Bob be younger? The asymmetry resolves because Alice accelerates. She changes frames of reference when turning around. She's not always in an inertial frame. Bob never accelerates, ignoring Earth's rotation and orbit. The acceleration makes the situation non-symmetric. Alice genuinely experiences less time. The effect is real. This has been confirmed with particle accelerators. Unstable particles, muons, created in high-energy collisions live longer when moving at high speeds, exactly as time dilation predicts. Muons created in Earth's upper atmosphere by cosmic rays traveled to the surface before decaying, impossible at their normal lifetime, unless time dilation extends it. In 1915, Einstein extended relativity to include gravity, general relativity. Gravity is not a force pulling objects together, it's the curvature of space-time caused by mass and energy. Massive objects bend space-time. Objects follow curved paths through this bent spacetime, what we perceive as gravitational attraction. And crucially, time runs slower in stronger gravitational fields. This is gravitational time dilation. Near Earth's surface, time runs slower than at high altitudes. The effect is tiny, about 1 second per 10 million years for every kilometer of altitude difference. But it's measurable. In 1976, the Gravity Probe A experiment launched a hydrogen maser clock to 10,000 kilometers altitude on a suborbital rocket. The clock ticked faster than ground-based clocks by exactly the amount general relativity predicted. The effect increases with gravitational field strength. On Earth's surface versus GPS satellite altitude, 20,200 kilometers, gravitational time dilation causes satellite clocks to run 45 microseconds per day faster. On the Sun's surface, time runs 0.002% slower than in deep space. Not much, but measurable with atomic clocks. On a white dwarf, a stellar remnant with mass comparable to the Sun compressed to Earth size, time runs about 0.03% slower. On a neutron star's surface, time runs 20 to 40% slower, depending on the star's mass. At a black hole's event horizon, gravitational time dilation becomes infinite. Time, as measured by a distant observer, stops completely. In 1959, physicists Robert Pound and Glenn Rebka performed a precision test of gravitational time dilation using a 22.5-meter tower at Harvard. They used the Mossbauer effect, gamma rays emitted and absorbed by atomic nuclei with extraordinarily precise energies. Gamma rays emitted from the tower's top and detected at the bottom were blue-shifted, higher frequency, by exactly the amount gravitational time dilation predicted. Why? The top of the tower is slightly farther from Earth's center, weaker gravity, faster time. Photons emitted there had to climb down the gravitational potential, gaining energy, blue shifting, as they descended into stronger gravity where time runs slower. The frequency shift was 2.5 parts in 10 to the 15th, incredibly tiny, but Pound and Rebka measured it with 1% accuracy, confirming Einstein's prediction. This result, along with Mercury's perihelion precession and gravitational light bending observed during solar eclipses, established general relativity as the correct theory of gravity. Time dilation was no longer speculation. It was measured fact. The global positioning system provides perhaps the most practical demonstration of time dilation. GPS works by timing radio signals from satellites. Each satellite broadcasts its precise time. Your receiver compares signals from multiple satellites, calculates the time delays, and determines your position. This requires nanosecond precision. Light travels 30 centimeters in 1 nanosecond. Timing errors of microseconds mean position errors of hundreds of meters. GPS satellites orbit at 20,200 kilometers altitude, moving at 3.87 kilometers per second relative to Earth's surface. Two relativistic effects compete: special relativity, velocity time dilation. Moving clocks run slow. At orbital velocity, satellite clocks lose about 7 microseconds per day. General relativity, gravitational time dilation, weaker gravity at altitude means faster time. Satellite clocks gain about 45 microseconds per day. Net effect, satellite clocks run 38 microseconds per day faster than ground clocks. Without corrections, GPS positions would drift by 10 kilometers per day. The entire system would be useless within hours. GPS receivers apply relativistic corrections continuously. Every navigation calculation accounts for Einstein's equations. Time dilation is not academic theory. It's operational necessity. Particle accelerators provide laboratories for extreme time dilation. At CERN's Large Hadron Collider, protons circulate at 99.9999991% the speed of light, just 3 meters per second slower than c. At this speed, gamma equals 7,460. Time dilation factor, 7,460. Particles that normally decay in microseconds survive for seconds in the lab frame, circulating billions of times before decaying. Muons provide a classic example. Created in the upper atmosphere by cosmic rays, muons have a half-life of 2.2 microseconds. At light speed, they should travel only 660 meters before half decay. Yet muons created at 10 kilometers altitude reach Earth's surface regularly. Time dilation extends their lifetimes by factors of 20 to 50, allowing them to traverse the atmosphere. From the muons reference frame, their lifetime is normal, but the atmosphere is length contracted to just hundreds of meters thick, so they cross it before decaying. Same physics, different perspective. Both explanations are correct and consistent. Particle physics depends entirely on time dilation. Detectors are designed accounting for particle lifetimes extended by velocity. Collision energies are calculated using relativistic mass energy. Every particle physics experiment confirms time dilation thousands of times per second. White dwarfs, stellar remnants with solar mass compressed to Earth size, produce measurable gravitational redshift. Light climbing out of a white dwarf's intense gravity well loses energy, shifting to longer, redder wavelengths. In 1925, astronomer Walter Adams measured spectral lines from Sirius B, a white dwarf companion to Sirius A. He found the lines shifted redward by about 6 parts in 100,000, matching general relativity's prediction. Modern measurements confirm this across dozens of white dwarfs. The effect is stronger for neutron stars. Spectral lines from neutron star surfaces show redshifts of 20 to 40%, depending on mass and radius. This gravitational redshift is time dilation made visible. Atoms on the surface emit light at a certain frequency, but to distant observers, time runs slower on the surface, so photons arrive with lower frequency, longer wavelength. Every photon carries information about time dilation at its emission point. Pulsars, rotating neutron stars, act as cosmic precision clocks, emitting radio pulses with millisecond regularity. Binary pulsars in elliptical orbits provide natural laboratories for testing gravitational time dilation. As a pulsar orbits its companion, its distance from the companion varies. When closer, it experiences stronger gravity and time dilation. When farther, weaker gravity and less time dilation. This causes systematic variations in pulse arrival times, Shapiro delay. PSR J0737-3039, a binary pulsar system where both neutron stars are visible as pulsars, shows this effect clearly. Pulse arrival times vary precisely as general relativity predicts, accounting for gravitational time dilation varying throughout the orbit. The match between observation and theory is exact to better than 1%, providing stringent tests of general relativity in strong gravitational fields. Black holes represent time dilation's ultimate extreme. The Schwarzschild radius, or event horizon, for a black hole of mass m is Rs equals 2gm divided by c squared. For a solar mass black hole, Rs equals 3 kilometers. For Sagittarius A star, 4 million solar masses, Rs equals 12 million kilometers. At the event horizon, gravitational time dilation becomes infinite. From a distant observer's perspective, time stops. Imagine watching someone fall into a black hole. You'd see them approach the horizon but never cross it. They'd appear to slow down asymptotically, redshifting increasingly as photons climbing out of the deepening gravity well lose energy. Eventually, they'd fade from view, not because they cross the horizon, but because photons become too redshifted to detect. From the falling person's perspective, nothing special happens at the horizon. They cross in finite proper time, perhaps in seconds for a stellar mass black hole or hours for a supermassive black hole. This apparent paradox, infinite time for distant observers and finite time for the infalling observer, reveals time's relative nature. There's no universal now. Events simultaneous in one reference frame occur at different times in another. Gravitational waves, ripples in space-time from accelerating masses, directly demonstrate spacetime's dynamic nature. When LIGO detected gravitational waves from merging black holes in 2015, the signal showed time dilation effects. As black holes spiral together, they orbit faster and faster. The gravitational wave frequency increases, the chirp. But near merger, immense gravitational fields cause significant time dilation. The chirp encodes information about space-time curvature and time flow near the black holes. By analyzing the chirp's evolution, physicists extract the black hole's masses, spins, and distance, all dependent on correctly accounting for time dilation in extreme gravity. Gravitational waves themselves are distortions in spacetime, literally ripples in the fabric of time and space, propagating at light speed. When a gravitational wave passes through LIGO's arms, it stretches and compresses space itself, changing the light travel time between mirrors and creating the interference pattern that signals detection. Time and space are not rigid stage. They flex, curve, and oscillate. Einstein's equations predict that rotating masses drag space-time around with them, frame dragging, or the lens-theoring effect. Near a rotating black hole, space-time itself rotates. Objects trying to remain stationary are swept along. This affects time. Close to a rotating black hole's event horizon, an observer rotating with spacetime experiences different time flow than one resisting the rotation. Gravity Probe B, a NASA satellite launched in 2004, measured frame dragging around Earth. Gyroscopes aboard the satellite precessed by 37 milliarcseconds per year due to Earth's rotation dragging spacetime. The measurement matched general relativity's prediction with 19% accuracy, limited by technical issues with the gyroscopes, not the theory. Frame dragging shows spacetime is not passive. Mass energy curves it, rotation twists it, and time flows differently in the twisted spacetime. On cosmic scales, the universe's expansion affects time. Light from distant supernovae is stretched by cosmic expansion, cosmological redshift. But the light curves, brightness over time, are also stretched. A supernova that brightens and fades over 20 days in its rest frame appears to brighten and fade over 40 days when observed at redshift z equals 1, look-back time approximately 8 billion years. This is cosmological time dilation. The universe's expansion stretches time intervals along with wavelengths. Observations of hundreds of distant supernovae confirm this effect precisely. Time really does flow differently across cosmic scales. This has profound implications. There's no universal cosmic now. Different reference frames moving through expanding space have different definitions of simultaneous events across cosmic distances. Einstein's insight united space and time into space-time, a four-dimensional continuum. Events are points in spacetime, specified by four coordinates, 3 spatial, x, y, z, and 1 temporal, t. The interval between events, the spacetime distance, is given by delta s squared equals c squared times delta t squared minus delta x squared minus delta y squared minus delta z squared. This quantity is invariant. All observers agree on it, even though they disagree on delta t, time interval, and delta x, delta y, delta z, spatial intervals individually. Different observers slice space-time differently into space and time, like rotating a book changes which dimension appears as width versus height. There's no absolute simultaneity. Events simultaneous for one observer occur at different times for another moving relative to them. Past, present, and future are observer-dependent concepts, not universal truths. This seems abstract until you consider implications. Somewhere in space-time, now, to some observer, includes what you consider future. The future already exists in space-time. We're simply moving through it along our world line. If past, present, and future all exist in space-time, time's flow might be illusory. The block universe interpretation suggests all of space-time, past, present, future, exists simultaneously as a four-dimensional structure. Our consciousness moves through this structure along our world line, creating the subjective experience of time's passage. This is philosophically challenging. It suggests determinism. The future already exists, fixed, unchangeable. Free will becomes problematic. But physics doesn't require this interpretation. It's one way to understand relativity, not the only way. Alternative interpretations preserve time's flow while accommodating relativity's lessons. The debate continues among philosophers and physicists. What's undeniable, time is not the universal river it appears. It's local, relative, dependent on motion and gravity. Relativity distinguishes proper time from coordinate time. Proper time, time measured by a clock moving with an observer, what a wristwatch shows. Invariant, all observers agree on an object's proper time elapsed between two events along its world line. Coordinate time, time assigned to events in a specific reference frame's coordinate system, frame-dependent. Different observers assign different coordinate times to the same event. Only proper time is physically meaningful. Coordinate time is a bookkeeping tool. When we say time slows in strong gravity or at high velocity, we mean an object's proper time elapses more slowly than coordinate time in some chosen reference frame, typically one at rest far from gravitating bodies. But there's no absolute reference frame. Each observer's proper time is equally valid. Time dilation is real. Proper times genuinely differ for different world lines between the same events, but it's relative. There's no privileged frame where time runs normally. Time dilation isn't just theoretical curiosity. It enables technology and constrains future possibilities. GPS and navigation, already discussed, relativity is essential for satellite navigation systems. Particle physics, accelerators and detectors designed accounting for time dilation effects on particle lifetimes and collision kinematics. Precision timekeeping, atomic clocks at different altitudes or in motion must account for time dilation when synchronizing. Future space missions, missions to high-gravity environments near neutron stars, black holes, must account for time dilation affecting communication delays and aging. Interstellar travel, if humanity develops near-light-speed propulsion, time dilation becomes crucial. Travelers age slowly, Earth time passes rapidly. A voyage to Proxima Centauri, 4.24 light-years, at 90% light speed takes 4.7 years Earth time, but only 2 years for travelers. Round trip, 9.4 years Earth time, 4 years traveler time. Returning travelers find Earth aged nearly a decade, while they aged 4 years. Time dilation offers a potential solution to interstellar travel's challenge. Even at light speed, crossing the galaxy 100,000 light years takes 100,000 years Earth time. But for travelers at 99.9999% light speed, gamma equals 707, subjective time is only 140 years. At 99.999999% light speed, gamma equals 2,236, subjective time drops to 45 years. In principle, travelers could cross the galaxy within a human lifetime, from their perspective. But Earth would age 100,000 years. Everyone they knew would be dead. Civilization would have risen and fallen multiple times. This is time travel to the future, in a sense. No paradoxes, no violations of causality, just extreme time dilation. The catch, reaching such velocities requires enormous energy. Accelerating a 1,000-ton spacecraft to 99.9999% light speed requires energy comparable to global civilization's output for years. But if energy becomes abundant, fusion, antimatter, etc., time dilation makes interstellar travel potentially achievable within human lifespans for the travelers. Advanced civilizations might harness time dilation for computation or longevity. Consider orbiting close to a black hole's event horizon. Time runs slowly. 1 hour near the horizon might equal years or decades far from the black hole. You could orbit for subjective hours while the external universe ages centuries. Return to find technological civilization advanced dramatically. This is a form of time travel to the future, in a sense. No paradoxes, no violations of causality, just extreme time dilation. The catch, reaching such velocities requires enormous energy. Accelerating a 1,000-ton spacecraft to 99.9999% light speed requires energy comparable to global civilization's output for years. But if energy becomes abundant, fusion, antimatter, etc., time dilation makes interstellar travel potentially achievable within human lifespans for the travelers. Recent breakthroughs in gravitational wave astronomy, particularly LIGO and Virgo detections of merging black holes, provide data about strong field gravity and time dilation near horizons. Future detectors, LISA, space-based interferometer, will probe even closer to event horizons, testing general relativity's predictions of time dilation to unprecedented precision. Relativity challenges the intuitive notion of time's flow. Physics equations treat time as a dimension, similar to space. We don't say space flows. We exist in three-dimensional space and can move through it. Similarly, we exist in four-dimensional space-time and move through it along our world line. The subjective experience of time's passage, the now moving through time, doesn't appear in equations. Physicist Julian Barber argues time is an illusion. What we perceive as time's passage is really changing spatial configurations. The universe is a vast collection of possible states, and our consciousness perceives sequences of these states as temporal flow. Others, like Lee Smolin, argue time is fundamental. Time dilation and relativity are real, but time itself is more than geometry. It's a dynamic process that gives reality its temporal character. Physics hasn't settled this question. Maybe time is fundamental. Maybe it's emergent from deeper physics. Maybe the question is meaningless. Time is simply one aspect of space-time geometry, neither fundamental nor derived. Inside a black hole's event horizon, space and time exchange roles mathematically. Outside the horizon, you can move through space freely, but are forced forward through time. Inside, you're forced inward toward the singularity, but can move through time in different ways, backward, forward, or at different rates. At least that's what the mathematics suggests. But time coordinates become spatial inside horizons. Radial position becomes time-like. The singularity isn't a place in space, it's a moment in time, an inevitable future you can't avoid, like tomorrow is inevitable for us. What does this mean for time's nature? Near the singularity, space-time curvature becomes infinite. General relativity breaks down. Quantum effects dominate. We need quantum gravity to describe what happens. String theory, loop quantum gravity, and other approaches suggest different possibilities. Maybe singularities don't exist. Quantum effects halt collapse before infinite density. Maybe time becomes discrete, quantized into Planck time intervals, 10 to the negative 43 seconds. Maybe extra dimensions open up, allowing escape from the singularity. We don't know. Black hole interiors remain the ultimate unknown. Time dilation allows travel to the future. Move fast or orbit near a black hole, and you age slowly while the external universe ages rapidly. But can we travel to the past? General relativity permits closed time-like curves, paths through space-time that loop back to earlier times. Certain space-time geometries, rotating black holes, wormholes, infinite rotating cylinders, contain such curves. But every known example requires exotic matter with negative energy density, which likely doesn't exist in sufficient quantities. Moreover, closed time-like curves create paradoxes. The grandfather paradox: travel back, prevent your own birth. How do you exist to travel back? Possible resolutions: consistency. Events self-arrange to prevent paradoxes. You can't kill your grandfather because physics conspires to stop you. Many worlds. Time travel creates branching universes. You travel to a different timeline where you can change history without paradox. Chronology protection. Stephen Hawking's conjecture that physics forbids closed time-like curves. Quantum effects destroy them before they form. Current consensus: backward time travel is probably impossible, though not definitively ruled out. Forward time travel via time dilation? Absolutely possible. Proven. Operational in GPS satellites and particle accelerators. Backward time travel? Possibly forbidden by laws of physics we don't yet fully understand. We've learned time is not the universal constant we intuitively believe. It slows in strong gravity. It slows at high velocities. It can effectively stop at black hole horizons. The evidence is overwhelming and diverse. GPS satellites requiring relativistic corrections, particle accelerators where unstable particles live longer, gravitational redshift from white dwarfs, pulsars in binary orbits, gravitational wave detections, cosmological dilation in distant supernovae. Every observation confirms Einstein's century-old insights. Time is woven into space-time's fabric. It bends with space, curves around massive objects, and flows at different rates in different circumstances. There is no universal now. Events that seem simultaneous to one observer occur at different times for others. Past, present, and future are relative concepts, not absolute truths. This transforms our understanding of reality. Time is not the stage on which events unfold. It's part of the play, dynamic and changeable. For practical purposes, time dilation matters. GPS navigation works because engineers account for it. Future space missions must plan for it. Interstellar travel, if it happens, will depend on it. For philosophical purposes, time dilation challenges our intuitions about causality, free will, and the nature of existence. If all of space-time exists as a four-dimensional structure, what does that mean for change, choice, and the passage of time? Physics doesn't answer these questions definitively. It tells us what time does, not necessarily what time is. What we know, time is flexible, relative, and profoundly strange. What we don't know, whether time truly flows, what happens to time at quantum scales, whether time had a beginning, whether it will have an end. The universe operates on clocks that tick at different rates. Time breaks near black holes. It stretches across expanding cosmic space. It slows for travelers moving fast through space. Time is not what we thought. It's richer, stranger, more wondrous than everyday experience suggests. Einstein showed us this truth, a century of experiments confirmed it, and we're still discovering its implications. Time bends, time slows, time breaks, and in breaking, it reveals the deeper structure of reality.